There we go. Okay. So yes, I'm Korey Haynes. I'm a grad student at George Mason University, and I'm doing research for my thesis at Goddard with Avi Mandel. And I'll be talking today about characterizing hot Jupiter atmospheres with WIFC-3 on Hubble. So you've heard quite a bit about transits. I won't go into a great detail here. We're doing transit spectroscopy. So I'll just reiterate that the more absorption of a given feature, the greater the transit depth we will see at that wavelength. So we've been exponentially growing the number of exoplanet transits that we know about, but constraints on atomic and molecular species are relatively rare compared to the total number of transits. I've just got some highlights listed here. This list is not exhaustive and clearly is a little bit out of date. So what I really want to just take away from here, though, is that despite the handful of different instruments we had NICMOS, some Spitzer, there's been ground-based spectroscopy, and photometric observations. You've heard about a handful of these kinds of observations already today. There's been a lot of back and forth. It seems whenever a new group observes a planet, we have to go back to the old observations and check them again. People don't always agree. And that's because we're really at the edge of what we can determine right now. Most of the instruments we're using were not designed for exoplanet transit observations, and so we're dealing with all kinds of systematics, and we just need to be very, very careful about determining our uncertainties and what we can really tell from these observations. So last year, Zach Berta published on GJ 1214. This was highlighted this morning. And more recently, Mark Swain published just this past spring on WASP 12, which you also just heard about in a different kind of observation. Swain's results have already gone public, and so I will be talking about our own reduction of those observations along with the ones from our program. So WIFC-3 was installed on Hubble in May of 2009. It has both imaging and low-resolution slitless spectroscopy capabilities in the optical and the near-infrared, but I'm going to be talking about this G141 GRISM with wavelength coverage from 1.1 to 1.7 microns with a resolution of about 130. The great thing about this wavelength range is that it samples two different water bands, and so kind of regardless of how good our resolution is, we can always target the water bands versus the continuum and get a better idea on what's really going on here. I want to draw your attention here to these, the model transit spectra here. This is for a hot Jupiter with different C to O ratios. That's been a topic of discussion, is whether you can have these carbon-rich planets. And so you can see here that in our wavelength range, there is a break between the models, between a carbon-rich model here in green versus a carbon-to-oxygen ratio of 0.5 here in red. So we really should be able to tell the difference of what's going on here and break some model degeneracies. All right, so here's a first look at the data. As I mentioned, we have the WASP-12 observations that were actually taken by Mark Swain, as well as WASP-17 and WASP-19, which are part of a larger campaign by Drake Deming. And you see some pretty big differences right away. These big gaps are, of course, just breaks in our timing coverage caused by Hubble orbits, right? Every time it passes behind the Earth, we lose sight of our target for about 45 minutes. So that was anticipated, unfortunate, but anticipated for a single transit. What was unexpected here is this feature here that's going on. So it's very clear in WASP-17. It's also noticeable in WASP-19, and then not really present in WASP-12. These are caused by WIFC-3 buffer dumps. So it can only store so many files before it needs to sit there and write them out. And when that happens, there's some unfortunate systematics that end up hitting your data. These targets are all roughly the same brightness. Actually, I think they're very close. So it's mostly caused by your choice of observations, which is good because it means you can avoid them in the future once you know about them, which obviously we did not when we started. So WIFC-3 is a 1024 by 1024 pixel detector, but you have the option of only using smaller subarrays. You can use a 512, a 256, or a 128 square subarray, and then you don't have to worry about reading out the whole thing every time. Because it takes something like 10 minutes, maybe 9, to read out that 512 subarray. And that, obviously, since this is for WASP-12, causes some pretty big issues. A compounding factor is the peak count that you get. So the larger the count number, the more this effect kind of hits in. So WASP-17 lost out big time. It has the largest subarray size, as well as a pretty high peak value. WASP-19 uses this nice small subarray, but has a very high value, and WASP-12 nicely snuck in here, kind of hit the jackpot. But we have a whole bunch of these already, so we have to fix it. We can't just throw these data out. What do we do with them? When Zach Berter was observing GJ1214, he came up with a concept he called divide out of transit. Divide out, divide out. I'm in Canada, the joke works, right? So what you do is you average together the out-of-transit data to get basically a template for these systematics. They are very repeatable. That's the nice thing about them. And then you can divide each of your orbit periods by that model, and you pretty much get rid of the systematics. WASP-19 cleans up very nicely, WASP-17, and we perform the same operation on WASP-12, and it does look a little bit cleaner. So that's nice. We used an MC fitting routine. It's a standard Mandel and Egel light curves. So we do that for our, sorry, I should point out these are all our combined light curves. We've just summed up over all the channels to get the best signal to noise possible here. So we fit a light curve to our white light data, and we subtract it from the original data over here, and we get our systematics, basically. The residuals are hugely dominated by the systematics you saw earlier. These are not, obviously, on the same scale. WASP-12s are actually, they show a little bit of a downward trend, which is something else that we've noticed. But overall, they're pretty good. But you see this very clear imprint here on WASP-17, and again with 19. So we believe that these systematics are imprinted on all of the channels. They're just not quite as visible because of the the lower signal to noise. So when we fit our channel data, or when we bin up that into slightly bigger than a single channel, we can use these residuals as an additional fitting term. So we add the residuals, the systematics, back into our data and use some scaling factor. And that scaling factor is an additional open term when we fit. And so here's an example of that for WASP-17. You can see the data for a single bin in black overplotted with our final fit, where it scales those residuals, it scales the systematics. And it does a pretty good job of recapturing those. And so when you actually look at the at the residuals, you get something that's, again, pretty flat overall. But our troubles weren't done by just trying to get rid of the systematics. It turned out that WASP-12, after some initial observations, has a companion that was discovered. It's this guy here, and it's surprisingly clear in our direct image. And so we have to get rid of that because it's very close to the main peak, and has already been believed to probably wipe out some earlier publications that claim certain things about WASP-12. It really does change the game. So what we did to fit this is we used an uncontaminated PSF from WASP-19 in our case, and we said that it should have the same shape. Obviously, it's severely undersampled. You can pretty much count the pixels here. We can't really do a very good fit on our own. So we assume it's the same shape as an uncontaminated PSF from WASP-19. We place one of them under the main peak for WASP-12, another one under the peak for Bergforce 6. We determine the offset from the direct image. And then we just do a joint fit where the open parameters are the height of both of those PSFs. And you can see here I've got all of the various, it's all color coordinated here, but basically you can't see the difference between the black data and the red combined fit. So we think we're doing pretty good. And here are residuals, and you can compare the flux levels here for the residuals compared to the total peak. So that's pretty nice. Charging ahead. There we go. We've got some results. So it's a little bit of a busy slide here. In every case, we've got our data with uncertainties plotted in black, thrown up against a variety of models. So for WASP-12 and WASP-17, I'm showing models from Adam Burrows, which are largely showing differences in the temperature structure of the atmosphere. So you've got a solar isothermal model here versus something with titanium oxide. This would indicate a temperature inversion, and it would drop the expected height of the absorption features because they're not absorbing, they're an emission. Similarly for WASP-17, sorry, I actually believe this is solar plus titanium oxide, otherwise I'm not sure that makes sense. The other option is that you can add a haze layer to depress those features. Because in all cases, they are lower than what we would expect. We would expect to see more of an absorption feature from the water than we do. For WASP-19 here, I'm showing a different set of models. These are by Niku Madhusudan. And so here we're looking at different C to O ratios. So the oxygen-rich model with a C to O ratio of about 1/2 is shown in red, with a carbon-rich model down here. And we get a slightly better fit for the carbon-rich model, which plays into previous results. That was already an option. For WASP-12, similarly, there were famously, actually, Madhusudan et al. Had claimed to find the first carbon-rich planet, and that discovery of the contamination source near it kind of ruled that out. It made that it fit both the models pretty equally well. So I promised that Swain had also observed WASP-12, and his paper is now out. So these are the Swain 2013 results compared with ours. And I see here some of you noticing that they're not really the same. There is a total offset that you can see here if you look at our actual flux levels. I'm not as concerned about that, only because I think Swain and myself are locking a lot of the basic orbital parameters to the literature values. With those breaks in the coverage on the light curve, we're just not able to constrain a lot of numbers. And changing those even slightly can change your overall transit depth. The more interesting question is the morphology of this spectrum, which also does not agree. And it's basically this feature here that we're both concerned about. As far as I could understand from Swain's paper, I don't think there's a very good physical explanation for what's going on here. That said, our uncertainties at this point are probably underestimated because of that contamination source. And I strongly suspect that that's the problem. From reading his paper, I do believe that we are approaching our data reduction in a very similar fashion. I even like to think that we're actually approaching the contamination fitting in a similar way, although we're using different templates for that PSF, but we're both using an uncontaminated source as our template. And if that's the case, then I'm not honestly sure what we can do with these particular observations, and I think we just need to be more careful in the future, especially with that contamination source so nearby. So in the future, the data is actually piling up in the archive. More and more people are using WFC3 to do transit observations. And so by combining more of them, we can get a greater range of parameter space for these planets instead of just 3, especially the 3 I've shown, which are honestly very similar planets in a lot of ways. And then, of course, always propose for more data. If we can increase the signal to noise on our transits, especially by stacking transits, Zach Berta had 3 transits he was able to stack for GJ1214. And with only 1, as I said, those breaks in coverage really do affect your uncertainties. It's very hard. You can imagine that obviously there are problems when you don't have a full transit, really, when you're looking at it. And then also secondary eclipses to constrain the temperature structure of the atmosphere. Here's just an example of WASP-33b, where you can see the inverted temperature structure in red and no inversion in blue. And while at the Spitzer band passes, there was a lot of overlap between the 2 models. The WFC3 data can really constrain, can really pick out one model over the other. So we hope to be able to do that kind of study in the future. And I'll stop there.
Thank you for a great talk. Questions? There must be questions. Yes.
Hey. I've actually got a couple of questions. Firstly, have you considered using something like Gaussian processors for removing your systematics from the wide field camera data?
Yeah, so we did look at fitting them. It hasn't worked out that well in the past. I'm certain we could go into it in more detail, but in general, just doing what we have done using the systematics themselves, the out-of-transit data, has seemed to give a cleaner result than any kind of fitting that we were able to accomplish.
Okay, my second question was, you mentioned the possibility of a hint of a high carbon to oxygen ratio in WASP 19. Mm-hmm. Is that because of its quite flat spectrum in wide field camera 3? Could that not be produced by cloud as well?
Yes.
Yeah.
Yes.
Okay.
Most of our observations can be reproduced by just adding a haze layer that depresses all the features, and you end up with a mostly featureless flat spectrum. So it's, we're leaving. It doesn't exclude these models for sure. There's a lot of open possibilities.
Thank you.
Mm-hmm. And at the top there, I believe.
Thank you. I was wondering about this apparently puzzling feature, what 1.2, 1.3 micron, which also actually seems to be commonly present in all of your WASP data of all of the different WASP objects, which actually to me looks exactly coincident to the J-band flux peak that's known from cool stellar and brown dwarf spectra, which corresponds to the gap in opacity between the water vapor bands. It appears to be not to be exactly reproduced by the models, but did you investigate if you can reproduce that with possibly different water abundances, different oxygen abundances?
I'm sorry?
Normally you have an opacity window at 1.2 to 1.3 micron, yeah. So I would actually expect to see that in the transmission spectrum. Yeah, there, and just
You're talking about the...
have it in your data in...
Right here?
In WASP 12, WASP 17, I think it was 19, it's not... Yeah, it also seems to be there.
Yeah, there's...
So do you have an explanation why the models might underestimate this transmission?
I'm sorry, I guess I'm still not understanding the question there. Why they're underestimating the transmission during the continuum level, or?
Yeah, maybe the continuum level is too low in the models.
I'm sorry, I guess I'm just still not.
Well, I would just expect to see a clear structure due to the water bands in the models. So I would like to understand why it's not seen in any of those models.
I guess I'm not entirely sure. I mean, the models were, as I said, I mean, these are from, I guess I don't have much of a hand in creating the models. I mean, they're Adam Burrows and Nika Madhusudan's work, so I guess I'm not entirely sure. Sorry.
Okay, thanks.
Hi, I'd like to bounce on the comment that you had that the offset between, for example, Swain and a new result could be due to orbital uncertainties. What level of uncertainty do you need to actually avoid this? Because that could become very important for Rayleigh scattering observations, for example.
Yes, I agree. So I guess I'm not sure offhand. We've experimented with a lot of stuff because depending on how much coverage you get on the transits, we should have been able to constrain some of those orbital parameters. And so we did experiment with leaving various different ones open. I mean, the Mandel and Egel light curve has, like 11 or 12 parameters that you can play with. So it depends on which of those you think you can constrain or not. The big ones that we kept playing with were just limb darkening, for instance. It's a problem because the Claret models that we ended up using, they're not particularly, you do have a fair amount of wiggle room in those once you add in uncertainties. And so I certainly can't give you a number, I guess. But yeah, I think you need to know them fairly well. Like I said, we're less concerned about that than maybe we should be because we're really interested in just that differential number more so than getting an absolute value on the transit depth. Sorry.
No one else? Okay. Well, let's thank Korey again.